Hello and welcome to the Neuron. Today we are going to learn one of the most important topics in cardiology, the electrocardiogram or ECG. First, we will start with an overview of ECG leads. ECG leads are essentially the eyes through which we can observe cardiac activity. Imagine the heart enclosed in a sphere with leads acting as tiny specific windows through which we can view electrical activity in specific parts of the heart. There are 12 ECG leads in total, divided into two main groups, limb leads and chest leads. Limb leads are applied to the arms and legs, while chest leads are placed directly on the chest. We will explore the exact placement of these leads later in the video. Limb leads include lead 1, 2, 3 along with lead AVR, AVL and AVF. Chest leads are comprised of lead V1 to lead V6. This is how we see leads on the ECG paper. You will find lead 1, 2 and 3 in the left corner of the paper. Right beside the lead 1 on the right side is lead AVR. Directly below the AVR is lead AVL and below that you will find lead AVF. Here is an easy way to remember this arrangement. Think about hand dominance. Most people are right-handed, fewer are left-handed and even fewer use their feet to write. Similarly, AVR is at the top, AVL is just below it and AVF is at the bottom. Leads V1 to V6 follow this sequence in an orderly manner. Now let's discuss what each of these leads show us. Lead 1, AVL, V5 and V6, these leads provide the view of electrical activity in the lateral part of the heart. Lead 2, 3 and AVF, these leads observe electrical activity in the inferior part of the heart. Lead V1 and V2 observe electrical activity in the septal part of the heart. Lead V3 and V4 observe electrical activity in the anterior or right ventricular part of the heart. Lead AVR views the posterior part of the heart. Here I have made a simple mnemonic to help you remember which ECG leads corresponds to specific parts of the heart's activity. This is a lion waving a final goodbye because he is fatally wounded by a spear piercing through his body from the lateral side. The spear lies mainly in the areas corresponding to lead 1, AVL, V5, V6. These leads represent the lateral part of the heart. One of the lion's anterior leg is at the bottom of the ECG, while the other anterior leg is at the right corner of the ECG paper. This hand is waving goodbye to us. Lead V3 and V4, which are located here, are the anterior leads. The nasal septum of the lion is aligned with the lead V1 and V2. Thus, lead V1 and V2 are the septal leads. The lion's tail corresponds to lead AVR on the ECG, making the lead AVR your posterior lead. There is a ditch on the left side of the lion corresponding to lead 2, 3 and AVF. So lead 2, 3 and AVF are the inferior leads. I have drawn this picture to help you practice the placement of the leads here. Now let's move on to the placement of the leads. It's important to note that traditionally there were 6 limb leads. Nowadays, these 6 limb leads are consolidated into 4 leads, which are attached to the arms and legs. However, the computer interprets these 4 leads and displays them as 6 distinct leads. Lead 1, 2, 3, AVR, AVL and AVF. With that in mind, these 4 limb leads are attached to the arms and legs. To remember the color coding easily, think about the mnemonic RBGY, which is similar to the acronym OBGY for obstetrics and gynecology. Just change O to an R and you will have RBGY. Here is how the color coding works. The R is red. Since R also starts right arm, attach the red colored lead to the right arm. Now make U pattern from right arm to the left arm. Now B is blue. Following the U pattern, attach the blue colored lead to the right leg. G is green. Place the green colored lead on the left leg. Y is yellow. Finally, yellow colored lead goes on the left arm. Now let's discuss the placement of the leads on the chest. Lead V1 is placed in the fourth intercostal space to the right side of the sternum. Lead V2 is also placed in the fourth intercostal space but on the left side of the sternum. Lead V3 is placed directly between lead V2 and lead V4. Lead V4 is placed in the fifth intercostal space at the mid-clavicular line. Lead V5 is placed horizontally in the line with lead V4 on the left anterior axillary line. Lastly, lead V6 is placed in the line with lead V5 along the mid-axillary line or directly underneath the midpoint of the armpit. Now let's move to the ECG paper. ECG paper is composed of large squares, each measuring 5 mm in width and height. These large squares are further divided into small boxes, each with dimension of 1 mm in both height and length. Each 1 mm length of a small box represents 0.04 seconds of time, so a large square being 5 mm represents 0.2 seconds or 200 milliseconds. To represent 1 second on ECG paper, it takes 5 large boxes. So, I have made this box sequence of 5 large squares on the diagram to demonstrate 1 second on ECG. Also remember that the height of a small square corresponds to 0.1 milliwatt. Thus, the height of a large square equates to 0.5 milliwatt. Now let's move to the PQRST wave pattern of the ECG. The P wave indicates atrial depolarization. The QRS complex represents ventricular depolarization, and the ST segment and T wave represent ventricular repolarization. Let's take a closer look at these components. Starting with the P wave, which signifies atrial depolarization. The normal duration of P wave should be less than 0.12 seconds or fewer than 3 small boxes on ECG paper. The normal amplitude should be less than 2.5 mm or 2.5 small boxes. If the duration and amplitude exceed these normal values, it suggests that the ECG is abnormal. Now, let's move to the PR interval. The PR interval represents the transmission of the cardiac action potential from the atria to the ventricle via the AV node. The normal duration of PR interval is between 0.12 to 0.20 seconds, which equates to 3 to 5 small boxes on the ECG paper. A shortened PR interval may be observed in conditions such as Wolff-Parkinson-White syndrome. PR interval may lengthen in case of heart block, digitalis toxicity, and Brugada syndrome. Now, let's move to the QRS complex. The QRS complex represents ventricular depolarization. It is considered normal if the duration falls between 1.5 to 2.5 small boxes. The amplitude should be exceed 5 small boxes in at least one limb lead and more than 10 small boxes in at least one chest lead. The upper limit of the QRS complex is defined as less than 25 small boxes. Moving on to the T wave, which reflects ventricular repolarization. The T wave's deflection should align with the direction of the QRS complex. For example, if QRS complex is positive, the T wave should also be positive. Normal T waves are upright in lead 1, 2 and V3 to V6, inverted in lead AVR and variable in leads 3, AVL, AVF and V1, V2. The amplitude of a normal T wave should be under 5 mm or 1 large box in limb leads and under 10 mm or 2 large boxes in chest leads. Now let's move to the ST segment. ST segments represent the interval between the ventricular depolarization and repolarization. We'll talk about ST segment elevation and depression in part 2 of our ECG series. Now let's discuss some abnormal waves found on the ECG. First, we have the Osborn wave, also known as J wave, which appears at the J point, the junction between QRS complex and ST segment. The Osborn wave or J wave is particularly noticeable in inferior lead and lateral lead such as lead 2, 3, AVF, lead V4, V5 and V6. This wave is a key indicator in patients with hypothermia, specifically when the body temperature falls below 32 degrees Celsius. Additionally, the Osborn wave may also be observed in conditions like hyperkalemia, subarachnoid hemorrhage, and certain cardiac arrhythmias. Moving on to the second abnormal wave, which is delta wave. Delta wave looks like a slope on the QRS complex. This is the characteristic sign of Wolff-Parkinson-White syndrome or WPW syndrome. We will talk about this syndrome in part 2 of our ECG series. Lastly, we come to the epsilon wave, indicating arrhythmogenic right ventricular dysplasia or ARVD, also known as arrhythmogenic right ventricular cardiomyopathy. This condition involves the replacement of the right ventricular muscle by fatty or fibrous tissue, leading to arrhythmias. Now let's explore the normal wave patterns and R wave progression on ECG paper. In a typical ECG from a healthy individual, you will see this type of wave patterns. Now let's see R wave progression from lead V1 to V6. You will notice that the R wave size is gradually increasing from V1 to V4 or V5. However, the height of the R wave decreases in V6 due to the resistance provided by the tissue and bone, which results in less electrical activity being captured in lead V6. Regarding to the T wave, it does not exceed 2 large boxes, which align with our earlier discussion on the normal measurements. Now let's discuss the normal axis of the ECG, which ranges from -30 to 90 degrees. If the axis of the electrical activity shifts right between 90 to 180 degrees, it indicates right axis deviation. Likewise, a shift from -30 to -90 degrees is termed as left axis deviation. In the normal ECG, most of the time lead 1, 2, 3, AVL and AVF typically show positive deflection because they align with the axis direction. If a particular lead is positioned beyond approximately 90 degrees of this axis, it will display a negative deflection. For example, the deflection in the lead AVR is negative because its direction is beyond the 90 degrees of the cardiac axis direction, which is a normal finding because in a normal ECG, AVR have a negative deflection. Now let's move to the final topic in the basics of ECG, naming the QRS complex. For naming the QRS complex, we need to remember these 3 basic rules. The first rule is that the first negative deflection below the baseline is called Q wave. The first positive deflection is called the R wave. If there is a second positive deflection, it will be known as R prime wave. The negative deflection following the R wave is called S wave. These rules apply to all the leads except lead AVR. Now let's look at the example. In the first example, there is only one wave and there is not any negative or positive deflection before or after it. So we will name it R wave. In the second example, a positive deflection is followed by a small negative deflection. So we will name it RS complex. The third example shows a minor positive deflection followed by a larger negative deflection. So we will name it RS complex. In the fourth example, there is a minor negative deflection followed by a positive and then the negative deflection. So we will name it QRS complex. In the fifth example, we will see a negative deflection then a positive deflection. We will name it QR complex. The sixth example shows only a single negative deflection. We will name it QS complex. Remember this. In the seventh example, a large negative deflection followed by a positive deflection is named QR complex. The eighth example reveals a positive deflection followed by a negative deflection and then other positive deflection. We will name it RSR prime complex, or we can also call it rabbit ear complex. In the ninth example, a small negative deflection is followed by a positive deflection. We will name it QR complex. In the 10th example, we will see a notch on the R wave. We will name it R wave with notch. In the 11th example, we can see R wave followed by a negative deflection that does not cross the baseline, and then there is a other positive deflection. We will name it R prime complex. Finally, the 12th example presents a fragmented QRS complex. So this is the end of the basics of ECG. Thank you very much for tuning in. If you found this video helpful, please don't forget to hit that like button and subscribe to my YouTube channel. Your support helps me bring more great content to you. Also, sharing this video with friends, family or colleagues who might get benefit from it means world to me. It's a great way to help me grow and continue provide you valuable educational content. Don't forget to follow me on the Instagram at @neuron5637. Thank you again for watching video and I will see you in the next video.